So we're going to look at some problems from the book here. If you have your textbook, you can join me on page 172. If you don't, well, you can just sort of follow along up on the screen and with the handout that I've given you. Yeah, I really think that maybe what I did was probably rush that lab a little bit. So let's just sort of go back a little bit here and try and look at some problems. Reading on page 172, it says, I haven't marked it yet. I just know that there were some struggles, that's all, right? But they seem to be a little bit more troublesome than usual. I mean, in the past, like usually I see the same trouble spots kind of thing. It seemed a little tiny bit more troublesome, and I thought, yeah, maybe.
You should make us one piece of paper with all the formulas on it.
You should do that.
You don't have to go back and forth.
No, you should get on that.
Isn't there one already? No?
Okay, so I'm reading on page 172, friction. Friction is the Jekyll and Hyde of forces. On one hand, we need friction to move. Without friction, the car would sit in one spot spinning its tires and a person wouldn't be able to take a step forward. But on the other hand, the motion of an object along a surface with friction causes the production of heat, a loss of mechanical energy, and general wear and tear on the object. The microscopic details of the force of friction are still not properly understood. In fact, and that is very true, that they really don't understand exactly what's going on at that microscopic level of friction. We believe that the two objects in contact make microscopic connections at various points on their surfaces. Even highly polished surfaces are rough and ridged microscopically. Because the contact points are so close together, intermolecular forces form microscopic welds that must be broken in order for the object to move. As the object moves, these welds form and break along the length of the path. So they actually believe that as you smooth it down, what happens is the surfaces get so close to each other that the molecules of the two surfaces actually there's some force between them. The magnitude of the frictional force is determined by the types of materials in contact and by the normal force exerted by one object on the other. Combining the two components to make up the frictional force, we obtain the following equation, and they write it as Ff equals mu Fn. Generally, though, it's written as mu equals Ff over Fn. That's usually how it's written, but it's the same formula, right? The Greek letter mu is called the coefficient of friction. It depends only on the kinds of surfaces in contact. The coefficient of friction has no units because it is a ratio of two forces, so it would be newtons over newtons. Okay? And then they talk here on the next page about kinetic friction, static friction, and I think you guys know all that kind of stuff. So let's just skip right to the example there, example number 8. Calculating the force of friction for a lawnmower being pushed. So a lawnmower of mass 12 kilograms is being pushed by a force of 150 newtons horizontally and 40 newtons down. If the kinetic coefficient of friction between wheels and grass is 0.9, which is pretty high, find the force of friction acting on the lawnmower. So they are trying to find the FF. So we've got a mass, and you guys have quite a bit of room there to write, I think.
No.
No? So we've got a mass of 12. We've got an applied force of 150 horizontally. And, well, maybe I'll call that FH. And I've got a vertical force of 40 newtons down. And I've got a mu value of 0.9, and we are to solve for FF. Okay, so what's happening is we've got one force sideways. I'm going to show it, even though it's a push, I'm going to show it as a pull, because that's what we do with 3-body diagrams. So I'm going to show 150 newtons like this, and I'm going to show 40 newtons down like that. That's my FV. This is my FH. And I also have a weight force down too, don't I? And a normal force up. Are there any other forces acting on the lawnmower? Just pause there for a second. Let's look at that. I got the applied force horizontally 150 newtons. I got a down force of 40 newtons. I got weight force down. I got normal force. Friction there. Very good. In fact, that's what they're asking for in the question, isn't it? Yeah. They're asking for the force of friction. Okay, so we need a bit of a plan here. To get if I've got mu and I'm trying to solve for FF, then using those two, right, using FF and mu, I would need the Fn, right? Now, it doesn't say anything here about constant velocity or not, does it? I don't know about you. Darren, you ever cut the grass? Yes. Do you start at one side of the lawn and then start really slow and then accelerate across the lawn?
No.
No, generally you sort of push the lawnmower at a constant speed, right? So in fact, I would say, if I was doing the question, I'd say, well, I'm going to assume it's a constant velocity, therefore, assuming constant velocity, that would mean what? What would have to be equal to each other? If it's moving at a constant speed sideways, the FH would have to be equal to the friction force, which would mean that the horizontal component, 150, is equal to my friction force. Right? Well, it doesn't really say it in the question, does it? But again, based on past lawn mowing experience, I would go with this. Now, having said all that, if you're following along in the book, it doesn't actually do that. And in fact, if you go to the next question, example number 9, it says find the acceleration of the lawnmower. So what does that imply? That it's accelerating, right? That it's not zero. It is dumb. Okay? But I've had kids say to me, what? Why is the lawnmower accelerating? I don't cut grass and accelerate. So that's why I talked about that briefly. So assuming that there is a constant velocity, the friction force would be that. I'll just draw a line there and I'll say, well, seeing as there isn't a constant velocity, we need to find the acceleration. So I'm going to, first of all, need to find the normal force, right? All right. So what is my normal force? Well, in this case here, the normal force up has to be balanced by what? Gravity and the weight force, right? So my normal force is going to be numerically equivalent to my weight force plus my vertical component. One's going to be opposite of each other, right? One's up, one's down, but numerically they're going to be equivalent to each other. So that's going to be mass times gravity, 12 times 9.8, plus my 40 newtons down, giving me 158 newtons of downward force, which means my normal force has to be 158 newtons up, right? Like if the book just sits on the table, that was silly closing. If the book just sits on the table, the normal force is equal to the weight force, right? But if I push down on it, well then the normal force has to be more, right? Because the book doesn't go through the tabletop. So now that I got that 158, now I go mu equals FF over Fn. 0.9 is equal to FF over my 158. And I get a friction force of 142. I get a friction force of 142 newtons. Okay, I can go to example number 9 now. Example number 9 is asking for the acceleration, right? Before I can get acceleration, I'm going to have to get what? Which formula has acceleration in it? F net. So I need to find the net force first. And the net force is going to be, if I got 142 to the left, and I got 150 to the right, my net force is simply my horizontal component plus my friction. I got 150 newtons sideways. I've got minus 142 because it's opposite. So I only get 8 newtons of force. And of course, now that I've seen my 8 newtons, now I can go F net is equal to MA. 8 equals my mass is 12. Solve for A. You get an acceleration of 0.7 meters per second squared. Okay, number 10. 2 people are pushing horizontally on a crate of mass 50 kilograms. One person pushing from the right with a force of 50. The other person is pushing from the left with a force of 80. Coefficient of kinetic friction is 0.3. Find the acceleration of the crate. Let's draw a picture first. These 2 people are foolishly pushing against each other. One is pushing from the right with a force of 50, which means that if it's from the right, then it's going left. How about we call that one F1? And then the other person is pushing the other way. I'll call this F2. Is 80, right? There is a weight force down. There is a normal force up. And there is friction. Now you should be able to tell right off the bat here, which way is this thing going to move? Right or left?
Right.
It's going to move right. I got 80 going to the right. I got 50 to the left. Obviously, it's going to go right. So there is, in fact, a little bit of friction going this way, right? Backwards. Do I need to worry about the up and down forces at all?
Nope.
They are balanced, right? I wouldn't say you don't have to worry about them completely. We'll see, right? We'll see. Do I have a frictional force? I have it. Do I have a value for it? I don't have a value for it, right? So I'm going to need FF equals, or mu equals FF
Yes,
over
sir.
Fn to get that. It probably is always a good idea just to find the weight force. Let's just do it. Get it out of the way. It's usually worth the mark. 50 times 9.8. 490, I believe. Right? Now you can write mu equals FF over Fn. The mu value is 0.3. Solve for friction force, 490. Giving me a friction force of 100. Doesn't make sense. 147, right? There we go. 147 newtons. That seems like a lot of friction, 147 newtons friction. Especially when you consider that these guys are pushing with 50 and 80. What's my net force? Like if there's no friction, it's going to be 80 to the right and 50 to the left, right? So my net force is going to be, I'm going to write F1 plus F2 plus FF, right? My horizontal net force is the sum of all the horizontal forces, the F1, the F2, and the friction. Well, it turns out that what you got here is you've got F1 is going to be minus 50, F2 is going to be plus 80, but my friction force is minus 147. This should ring some bells. This should be like, this doesn't feel right, something's going on here. The net force is minus 117 newtons. But where does the majority of that force come from? Like if I just deal with the 50 and the 80, I got 30 to the right and I got 147 of friction. Is there going to be 147 of friction? No, because remember, friction's kind of like teenagers. They only have to do as much as they have to. Not even a smile at anyone. A little shake of the head by Calvin. Yeah. So if I got 30 newtons of applied force, but I got up to a maximum of 147 newtons, guess what's going to happen? The acceleration is going to be 0. This thing is not moving. It's not moving. Before I go on, does this make sense? Why it's not moving?
Yeah.
Because there's more friction than there is force, right? It's like me going like this with one finger. It's not moving, right? There's friction there. But it's not going backwards, right? Yeah. Okay. Let's look at number 11 here. A 0.5 kilogram block is being slid up a chalkboard with an applied force of 6 newtons upward and 2 newtons toward the board. If the coefficient of friction is 0.4, calculate the acceleration of the block. So this one's turned sort of sideways a little bit. Right? So we've got a mass of 0.5. There's an applied force of 6 newtons upward. Let's call that FV is 6 and 2 newtons inward. FH is 2. And we need to find the acceleration of the block. There's also weight force down. Is there friction here? Yeah. Which way is it? Well, the block's going up, so the friction has to be down. Now, because I'm pushing with 2 newtons in towards the board, that means there's got to be a normal force. This really should be over here. Right? Should be shown as a push. FH is 2, and then the normal force would have to be 2, wouldn't it? Right? The normal force is always perpendicular to the surface. So here, the normal force is not equal to the weight force because it's a sideways kind of deal. Okay, so what do we start with? I need to find the acceleration of the block. The acceleration is upwards So I'm going to have a net force upward, so I got to come up with that first. But the first step is going to be figuring out what this friction force is. So mu equals FF over Fn. This is 0.4. Friction force is what I'm solving for. The normal force, again, is not equal to the weight force here. It's in fact equal to that 2 newtons of sideways, right? So I get a friction force there of 0.8. Now, am I going to have to know what the weight force is? Probably, right? I mean, the thing's going up. It's going to be balanced by gravity. Yeah, I got to find out what the weight force is. Let's just do that. Mass times gravity, 0.5 times 9.8, which is a convenient 4.9 newtons. We got to deal vertically now, so let's just say F net. My net force, my vertical net force, is going to be equal to the vertical component 6, and then these two red guys down here, plus the weight force, plus the friction force. They're both going to be negative because they're down. This is a W here. So that's going to be 6 minus 4.9 and minus my friction, 0.8. Is this thing actually going to move? Just barely, right? 0.3 newtons upward. Now I'm going to go F net is equal to MA. 0.3 mass, what was it?
0.5.
Oh, yeah. 0.5A. 0.3 divided by 0.5, acceleration 0.6. These aren't too bad, are they? Should I let you guys try the last one, do you think? No? Can you tell right away that it's harder? Last one. A puck of mass 0.3 kilograms is sliding along an essentially frictionless patch of ice at 6 meters per second. It encounters a rough patch of ice, and don't we all encounter a rough patch in our lives one time to time? No? Things are good? Good to hear. It encounters a rough patch of ice with a coefficient of kinetic friction of 0.1. How long will it take for the puck to stop, and how far will it travel? Doesn't this sound kind of familiar? Didn't we do one like this? Kind of, sort of. Except I think I just gave you the friction force, right? Now I'm going to just give you the kinetic friction. So let's just draw this out here. 0.3 is our mass. It has an initial velocity of 6. And a little bit later, it has a final velocity of 0. Right? And the only thing I know is I know that during that time it's slowing down and it has a mu value of 0.1. And that's all I know. Okay? So force-wise, I've got weight force down, I've got normal force up, and I've got friction force backwards, slowing it down. FF. Need to reorient. Okay. Hello. Okay. So let's start with our weight force. It's always the simplest thing, right? 0.3 times 9.8. 2.9 newtons is my weight force. That always leads you into the friction force. Mu equals FF over Fn. 0.1 is equal to FF over... Now, do we need to write Fn is equal to 2.9, do you think? Can we just sort of... We know, right? I think we know. So my friction force is 0.29 newtons. Is there any other sideways forces that need to balance that off or be accounted for? Any other sideways forces? And the answer to that is no. So I'm going to specifically say, therefore, the net force is 0.29. Right? There's nothing else slowing it down. That's the net force. The question is, how long will it take for the puck to stop and how far will it travel? So we're solving for T and we're solving for D. And the only way to get from all those force formulas to all those kinematics formulas is to use the bridging one, the one that connects them. F net is equal to ma. 0.29 is equal to my 0.3a, and you get an acceleration of almost basically 1, 0.97. Okay, and here's what I've been talking about. All of these questions lead into kinematics kind of questions, the kind that we did on the first test, right? So if you can show me that you now get these, maybe we can talk about that first test a little bit. Adjusting that mark of it. Okay, so if I'm looking for the time, sure, am I going too fast? So now that I've got my acceleration, if I'm looking for time, I can go something like Vf equals vi plus at. We know the final velocity is 0. We know the starting velocity was 6. My acceleration now, should that acceleration be negative?
Yeah.
It should, right? Is it going to be automatically negative? No, you have to make it negative, right? And I guess technically the place to make it negative is right there, right? Because really the friction force should be negative because it's slowing down, which would drop through here. But, you know, I don't think it's too big of a deal. But you have to realize that it's going to be negative. Okay, giving us a time of 6.2 seconds because it is slowing down. Okay, if you want to know how far it goes, that would be d equals vit plus 1/2 at squared. Initial velocity is 6, time is 6.2, 1/2 acceleration again minus 0.97, my time again 6.2, and I got to square that, squeeze that in. Oh, I had room. And you should get a distance of, make sure that's negative there, you should get a distance of about 19 meters. Okay, I'm going to be quiet. Here's some textbook questions you can try. If you have your textbook on page 188, numbers 39 to 48, if you want to go for a walk and get your book, that's a good idea. Okay, tomorrow we'll talk about some friction on ramps, which I really should have done before the lab. And then I'll give you some chance to work on some problems on Friday, when many of you are away.